I'm Bill Rader. I'm the Vice President of Design Engineering at Solana.
I'm Ryan Cabico. I'm the Application Engineer for FirePower products of Solana.
For our SL 2001 and 2002 products, we have evaluation boards that can be purchased. However, those boards don't have any heat sinks or thermal mitigation associated with them. So today we're going to talk about some of the work that we've done in experiments to prove out and verify the capability to switch at a higher frequency with improved thermal conductivity to a heat sink or a chassis. This particular board allows for components on both the top and bottom of the board. And you can see on the bottom of the board, there's a few components that are directly underneath the laser. And then there's a large area of exposed copper with thermal vias covering most of that area. We have designed a custom heat sink that, in this case, we made out of copper, 3 millimeter thick, and it can lie flush with the exposed copper on the bottom of the board, and then has cutouts in order to allow the components on the bottom of the board, as well as some connectors that we have on the bottom of the board. So basically, you can see here that heat sink gets mounted on the back of the board, and then we go in and we fill in the cutout area with a gap filler thermal interface material. In this case, we use one that has a thermal conductivity of 3.6 watts per meter Kelvin. Lastly, we have created some universal, larger heat sinks that can work with this board as well as other boards that we've designed that basically are meant to mimic this board being mounted onto a chassis with a good thermal conductivity to a further distance.
Here I have the sample board, which will show you the exposed copper at the bottom. So first, we can put the heatsink at the bottom, like this. And then we screw the board from the top side to align it. We apply the thermal compound on this portion of the board, fill it, and then we can mount this universal heatsink. The final assembly would look like this one.
So now Brian, he's going to show a setup that we have here that we've been running for the past few hours.
And I'm running it for 100 kilohertz. So as you can see, I have here the waveform. The yellow one is the VCAP and the blue one is the light pulse. So just to show you the frequency, it's showing 100 kilohertz, and then the light pulse is there. I'd like to show you how much the temperature is now using the thermal camera. So right now I am reading about 63 degrees Celsius for the hottest components on the board, which is the VCSEL.
This board has a 400 watt rated VCSEL on it that is commercially available and has an emitter area of about 0.6 millimeters squared. We've been working with the vendor of this particular VCSEL because with a very short pulse width that we have about 2.6 nanoseconds, we're able to get a peak power closer to 800 watts, and so almost double what the rating is. So this is, showing the conditions very close to what we're running at right now. We would say without any heat sink, this board, we can run it at 10 kilohertz for these conditions, but then if we move up to 20 kilohertz, the laser is getting a little bit too hot for us to be comfortable. So this is showing with the heatsink attached data for 10 kilohertz, 50 kilohertz, 70 kilohertz, 80 kilohertz, and 100 kilohertz, which is what we're running at right now. At 100 kilohertz, the laser temperature for this is pretty close to what Brian was just measuring. We are showing an input power of about 2.19 watts at 100 kilohertz, and we did not really a real theta JA calculation, just showing that 2.19 watts with the temperature rise of about not quite 20 degrees C that we're seeing on the laser itself.